All right, good morning, everyone, and thanks for coming and for your patience. Today, I'm really happy to be able to introduce Professor Randy Dumont from the chemistry department at McMaster. I've known Randy by name for more than 30 years, because as most of you know, I was obsessed with the tunneling time problem, and one of his papers was really one of the early seminal works on this back in the 1990s. And then I guess we met at some point after I moved to Canada 50 years ago when I was down at Mac. He was telling me about some really interesting calculations he started doing as he got excited again about tunneling.
Yeah.
So I thought it would be fun to hear more about that. Randy did his PhD here at UT in chemistry with Paul Brummer and postdoc at Columbia. And
Phil Pachukas. And then I've been at Mac since then. Yeah.
So please join me in welcoming him back to his old stomping grounds.
Okay, so I guess I'll open with I'll explain these pictures that I've featured here. Just local. I just like to put some pictures of the local where I've come from. So this is from the McMaster Museum of Art, and this is another art installation at McMaster, which is called Man Releasing Eagles. And the guy who made this, the artist, he actually was a professor at McMaster for many years, well, his entire career. And then this is just a picture of Lake Ontario. I thought just for local Hamilton. And this is at Stony Creek. Okay. Forward goes like this. Yes. Let's see. Okay. So we're talking about tunneling. I gave a talk 4 years ago here. I think it was an informal one. It wasn't like part of the series or something. And some of you may have seen it, but most of you didn't. So I'm going to have to go through that material again. Hopefully we'll have to make sure I got a lot of time for the new material. Anyway, so the entry point here is the McCall-Hartman effect. McCall wrote a paper in like 1932. Yeah, it was 1932, and then there was another paper in 1962 by Hartman, and the effect was long known as the Hartman effect because nobody had read the 32 paper. But actually, when you go back, oh, there it is. So I call it the McCall-Hartman effect now. So maybe some of you may have heard of the Hartman effect. Same thing. Okay. So what it is that if you look at a particle tunneling, if you can define the time, and that's a big question, which we can talk about, for time under the barrier that it's tunneling, what seems to be is that the particle spends very little time there. And in particular, at some point, and as you make the barrier wider, the time doesn't depend upon how wide the barrier is. So that's the McCall-Hartman effect. And this was observed experimentally here for ultra-cold rubidium atoms using Larmor times. Okay, so for this talk, our interest is in the possibility of superluminal velocities. And so what if we have like a really wide barrier? I mean, and the particle comes in really fast, like could it go faster than the speed of light? That's the question. Okay, so now there was a 2000, as far as I could tell, this is the earliest 2007 paper using stationary phase approximations to the Dirac wave packet evolution, which showed that yes, that could be. Okay. And so we further investigated that. Now, it turns out that the photon tunneling question had already been addressed much earlier in actual experiments. Enders and Nimst in 1992 and single photon experiments in 1993, Steinberg, Kuwat, and Chow. So we're going to, this is going to be theoretical. We're not doing experiments here. You wouldn't want me doing experiments. I would just break everything probably. So I wouldn't mind standing and watching you guys do experiments. That would be fun. Anyway, so we're going to calculate the arrival time distribution for a particle that tunnels through a barrier. So it's going to be initially localized. So one of the important things in the tunneling time question is sometimes people look at energy domain and like wave packets are already, the particle's already on the other side of the barrier. But I'm looking at localized. I want to know the particle's here, and then it's going to end up over here. And how long does that take? So we're going to calculate the arrival time distribution. And it's going to be done using Dirac dynamics. So this is the arrival time distribution is just the flux here. And the flux has this form in the Dirac formulation. So these are Dirac spinners. Okay, so I'm going to do 1 plus 1D Dirac equation to make it simpler. And then we're only going to look at one spin. So our spinners become two component vectors. And so this is the Dirac equation written in terms of these chunks of gamma matrices. And we can think about it as a Hamiltonian evolution, where this is the Dirac Hamiltonian here. This is like a sigma Z and a sigma X polymatrices that are in this operator. Okay, and then and I'm going to look at a rectangular barrier, so I can solve for the energy eigenstates exactly, analytically. We'll come back to why I can't really do this. I shouldn't be doing whatever. Okay, we'll come later. So anyway, we can do those. We can find those wave functions, and then we can get the time dependence of a wave packet by just doing an integral over energy. This is really an energy integral. Like it's not a momentum. It looks like momentum. I'm using P to parameterize because it's really convenient. The energy, the energies here, E of P. So these are energy eigenstates labeled by P, because P is always positive here, so we don't need negative P's, because these are energy eigenstates right here. Okay. All right, so we can solve this exactly, numerically. Well, exactly, like highly accurately is my point. Highly accurately. And we're also going to solve it using the method of steepest descent. The role of that will be, it actually gives us some insight into, you can see how the Hartman effect, McCall-Hartman effect pops out. Okay, as a matter of fact, right here. Okay, so when you do the steepest descent calculation, you get a nonlinear equation for the saddle point momentum, and written here. This is, of course, it's a nonlinear equation. You have to, but you can solve this by iteration, and it converges in like 3 or 4 steps. So it's actually pretty useful in this form. This tau is a complex phase time. The maximum of P occurs when the momentum is real, and that happens when T equals the real part of this tau. So that'll be our time that will end up being really fast, like a short time. And then the imaginary part of time enters, and it gives you a speed up effect, because the imaginary part is negative, and then you get a negative imaginary times an I, so you get a positive here. So P sharp is greater than P naught. The P naught is the initial momentum of the wave packet coming in. Okay, so we're going to do some numerical calculations, and these are our units here. We used reduced Compton wavelength for distance. That's lambda bar. It's sub picometer, and then the time unit is 1.3 zeptoseconds. So everything's really small. And then the energy unit is just the electron rest mass, because this is for electrons. Okay. If it was some other particle, you would just sub in the mass of the other particle and change the units. Everything else would be the same. Okay, so here's some results. So this is an incoming particle, electron, at 99% the speed of light. And then there's the initial, this is the width of the initial wave packet. This is the barrier height and the width of the barrier. So the magenta curve here this is a log plot. So I'm calling it P tilde, by the way, in these plots. Okay, so that'll be consistent, other than the very last slide where I didn't do it. P tilde would be, it's like a non-normalized probability distribution. That is to say, when you integrate it, you get the transmission probability. You don't get 1, because the transmission probability is quite small. And you can see that here with that this is really low. And you have to use a log plot, otherwise you wouldn't see anything. Now, if I normalize this, dividing by the transmission probability, that would be like post-selecting. That would be a post-selected distribution. Then I can compare them with a linear plot, and you can see that the magenta curve peaks earlier. That's the superluminal part. It peaks earlier than the other one, which is light. This cyan curve, by the way, I didn't say that. That's actually a photon in a vacuum. So there's your reference point, your luminal. And it's using with the same initial Gaussian wave packet. Okay. So we see some superluminality, apparently. Okay. Here's another one which has a bigger effect. Notice that to get a bigger effect, we have an even lower tunneling probability. So that's the way it works. The bigger the effect you want, the less likely it's going to happen. Okay, and then this shows the McCall-Hartman effect. You can see this is barrier width increasing, and you can the time under this is total time, but if you just subtract this, that's the time under the barrier effectively, and it plateaus. Depends on the barrier height, but it plateaus in every case. All right, so here we have superluminality. Yay, okay, that was a fun thing to have. Can we use it to do anything? Maybe not. Okay, that's a problem. Well, the first thing you might want to do is send a signal with these superluminal electrons. The trouble is the probability of tunneling is really small. Suppose it's 10 to the minus 6, which would actually be kind of a large value compared to some of the results that I've looked at. But let's say, so I'm sending this electron, but it probably won't get there anyway, because only 1 in a million. How would I get around that? Well, I could use 10 million electrons all in parallel at the same time. Then actually the probability of one getting to Ephraim, using the other side of the barrier, is actually quite high. It's almost 1. And if it's not good enough for you, just use 10 to the 8. And it's like, you get 0.999, a lot of 9s. I don't know how many 9s, a lot of 9s. Okay, so how does that work? Well, I define the first click distribution. That is, so I've got all these parallel experiments, and Ephraim there, he's got a first click, he's got the detector. He's got a lot of detectors, actually, one for each of my electrons. Now, most of them don't go off, but one of them does. And that's the first click, right? And once a click happens, he knows I sent a 1. Okay. Now, how does he know I sent a 0? Well, he won't get a click. Okay. And you might ask, how long does he have to wait? Not very long, turns out. Okay. He'll know that I didn't send an electron if he doesn't get a click by a certain time. Okay, so here's there's a formula for the first click distribution. And this in here is the probability that there's no transmission up to time t. Okay, so what are the properties of this distribution? Well, one is you can integrate it and get the normalization of it. It approaches 1 pretty fast as the number of electrons is large. Okay, so for 10 to the 7 electrons, and a transmission probability 10 to the minus 6, the probability of getting a first click is actually this, pretty close to 1, like I said. All right, so there's some more properties here. I don't want to spend too much time on this, but I just want you to know that I have formulas for like the mean of the first click distribution. I can understand that, and the width. Okay, but why don't we just look ahead, see what. Oh, but yeah, so one more property. This is very important. This is probably the most, that's why I emphasize this one. Now, we saw, going back, we saw these distributions. This is peak before this, but you'll notice that it never crosses the cyan curve at early times, okay? But if there were if you could change parameters, whatever, find some case where it did cross at some early time, then the first click distribution for the electrons would peak earlier than that for photons in a vacuum. So that would be superluminal signaling by my definition. Okay. Now it turns out, now I didn't really point this out, but I mentioned that I was doing steepest descent calculations, and you didn't see anything there because it was exactly, the curves matched exactly so you couldn't see, it was just one curve. But the model I used, I was doing steepest descent calculation for the most probable time, and then I was basically Taylor expanding the log of the probability distribution around there to get a Gaussian model. And that worked well, seemed to be pretty good. But If it were really good, then it should predict superluminal signaling. Because like here's just two upside down parameters. This is a log scale, right? And this one's peaked. It's lower, but it's peaked earlier. It crosses. It always crosses. If you think about parabolas, they will always do that. But in my numerical calculations, that never happened. I looked for that, obviously. I spent a lot of time and I couldn't see it and I couldn't understand what was going on. But then it was pretty clear what the problem was. That it was my steepest ascent approximation only at the most probable time. I did it so that I did the steepest ascent calculation at every time separately, and then the superluminal signaling goes away. So this was kind of an interesting result, I thought. And so the way to understand this is this real part of tau that I mentioned. Okay, so that's the time. That's the peak time, and here it is changing with time. Like, what does that mean? Okay. So what it means is for each time, I basically get an upside down parabola model. Okay. But for early times, it's a model that's good, just close to that time. So it's really modeling this part of the parabola that's not the middle part. And then this would be the peak of the parabola if it did extend. So in other words, there's distortion of the Gaussian model. It's just that it's pretty subtle and it's easy to miss. But you don't get superluminal. So I wrote a paper about that. It's subtitled the McCall-Hartman effect fades away at early times, and that's what this means. What am I doing for time now? Put this up. Wow. Okay. So here's some first click distributions. So this red curve here is the arrival time distribution for one electron. And this cyan curve here, the big one, is the arrival time for one photon in a vacuum. So there's no barrier for it. Also shown here is the steepest descent approximation. Now you see there's a difference. It turns out that there's actually an infinite set of saddle points, but I only consider the first one. That's a tunneling one. The others are associated with Bob barrier reflection, and they're associated with the long time tail here. Okay, but I don't bother doing those because we're interested in tunneling and the early stuff. Okay. Anyway, so we have those. And then we plug into the formula for the first click distribution, and here are the first click distributions for 1 trillion electrons or 1 trillion photons. And you see that the photon first click distribution is earlier, peaks earlier than the electron. So photons win. Okay. So what happens? We could have expected that, right? Maybe? I don't know. Okay. So what happens? This is peaking earlier than this, but when you increase the number of electrons, what happens to this curve? It goes up. It kind of goes up. And it isn't until it gets close to being normalized that it starts moving to the left. Whereas the photon one's already normalized, so it always moves to the left. So it will always peak earlier. Notice a few things about the first click distribution, which is not a bad idea for signaling, okay? Because, well, first of all, it peaks so early. And already you might be saying, wait a minute, aren't the photons superluminal here? And they kind of are, by my definition, okay? I don't know what that means, okay? That's a whole other thing. We'll talk about that afterwards. But it peaks, it's very sharp. These first click distributions are very sharp. And notice how they fall off really fast. So that's why there will be a time that if you haven't seen, like somewhere around here, if you haven't seen the electron, you're not getting one. It's not going to happen, okay? Probably just drops off a cliff. It's really convenient, actually, this kind of multiplexing. Okay, so that's one case. And then here's another one. So yeah, another one. But I looked for ones superluminal, you know, where the electrons win, they never win. Okay, it's very frustrating. Okay. This is just showing you how does this, what does this mean? Okay. Okay. This blue, these are all like, again, this is in the P data space. So this is showing you the P sharp trajectory as a function of time. And these are early times. And this purple line is superluminal. That's the speed of light, actually. So the points, they go out into this. Anything under here is superluminal, but when it goes out there, it's subluminal. I don't need to go back there. What am I doing? Okay. Oh, yeah. So there were two papers I just went through, actually, that we published. And the first one was actually featured on PBS Space-Time. And also there was an article in Quantum magazine about that. Okay, so that's what I talked about 4 years ago. For those who were here, you might remember. That was my talk 4 years ago. But what's wrong with what I just talked about? It turns out to have a problem. The barrier is too high and its edges are too sharp. So we know that electric fields exceeding 3 million volts per meter on air will cause the air molecules to ionize. And so that's the dielectric breakdown threshold for air. And what you get is lightning. If you have electric fields exceeding 10 to the 18 volts per meter, only 1 trillion times higher. Okay. It has to be pretty high. This will cause dielectric breakdown of the vacuum. So basically, vacuum lightning is possible. I saw it called sparking the vacuum. At least I thought I did. And then when I tried to search and find that, I couldn't find it. So I don't know. Okay, sparking the vacuum. I like that. Okay. So this effect is predicted by quantum field theory. And it's called the Sauter-Schwinger effect, or at least it is by some people. Some people just call it the Schwinger effect. Schwinger, basically, what he did was he calculated the continuous rate of electron-positron production associated with a constant electric field across all space. Okay. Now, it turned out that in the 1930s, this is analogous to the McCall-Hartman. That's why it's kind of fun. There's a kind of parallel. McCall, a guy named Sauter, actually wrote a paper in the 30s predicting this. And so now some people call it the Sauter-Schwinger effect, which is, I'm going to do that too. I'll do that too. So, but if you've heard of the Schwinger effect and you wonder, is this different? It's not. It's the same thing. Same thing. So what is this effect? Okay, I have to tell you something. So I gave this talk, not this talk, but the one up to here. 4 years ago, I had never heard of the Sauter-Schwinger effect then, because it's not something we learn in chemistry at all, really. Anybody, how many know the Sauter-Schwinger effect or Schwinger effect? Okay, so even physicists don't necessarily know that. Okay, so good that I'm here. I can teach you about it. Oh, that's kind of cool. So this effect, it's predicted by quantum field theory. Okay, and it cannot be neglected because my barriers are really high. Okay, they're above the threshold for this effect. Okay, so in quantum field theory, now I had to learn this stuff. Oh, it's so, I'm a chemist, right? So I had to learn quantum field theory in order to do this. And it took a while because most books, well, as far as I know, no books on quantum field theory actually do what I needed anyway. So you read a book and it's really thick and it's hard pretty much the whole way through. And then you get to the end, oh, they didn't actually do what I wanted. So, but I eventually learned this and how to do it. Okay, so what you do is you have your field operator, and it's written, it's always like this. It's a sum over positive energy states and negative energy states. And like, just think time equals 0 for a moment. Okay, so at time 0, this is an electron annihilation operator, and this is a positron creation operator. And this is positive energy states. So the positive energy states are electron states, The Q here is just a P and spin. It's just a sum, just so I didn't have to write two things all the time, just one. Okay. So these are positive energy states. These are electron states. The negative energy states are, if you apply charge conjugation to them, they're positron states. They're not actually, I saw in papers they're called negatron states, but my theoretical physicist colleagues at McMaster told me that's old-fashioned. Don't say that. But they're not exactly positrons by themselves. They're almost, you just have to do something to it. Take the complex conjugate mostly, that's what it is. Okay. Okay, so the field operator. So how do we do the time dependence of the field operator? So the time dependence goes into the field operator either in these creation and that's an annihilation and creation operators, or in these states here, which are wave functions, which I understand, well, those spinners, okay, but still they're things I understand better than quantum field theory in general. So you have a Heisenberg or a Schrodinger picture, and because they're the same, you can derive what the coefficients, like how you can expand what this annihilation operator looks like at time t. And the coefficients are just these green functions, these time-dependent green functions. And so what is this? So this one here says take an electron state at Q prime state and time propagate it, and then overlap with the Q positive energy state. And over here, and that just gives you, the coefficient for a new electron annihilation operator. But you get mixing of the electron and positron operators because of this and this term, these terms. So what happens is, here we're starting with a negative energy state, so we're starting with a positron, and we're time evolving it for time t, and then we do this overlap. And if we didn't have a supercritical barrier, this would just be zero, because the positive and negative energy subspaces don't mix normally. Okay. So it's the mixing which gives rise to an effect. Electron-positron pair production is what it is. So that's the fire, that's the sparking the vacuum. You get electrons and positrons coming out of the vacuum. And it doesn't violate energy conservation. It's because you have a very strong electromagnetic field, and the energy of the electromagnetic field is being converted into electrons and positrons. Okay, so I'm going to define these subspace projections. So this is what this is. What these things are going to be. They're two superscripts now. The one on the right is where we started. The one on the left is where we end up. So this is my evolving electron state time t, and this is the projector onto the positive energy subspace. But we could also project onto the negative energy subspace, and that would be this term. And again, this would normally be zero. But if you have a strong enough field, you can get something non-zero. Yes?
I'm just curious, it seems to me that this effect depends on how strong the field is. So as you said, how sharp the edges are, which is different to the first paradox that would have struck my mind, which is the Klein paradox, that I think depends only on the height of the vector. So are there problems that depend only on the height, or is everything really dependent on the thickness of the edges?
Well, it actually turns out that the edges are the most important thing, and that the reason the height has an impact is because they make the edges sharper. Okay, so if your edges are soft enough, it doesn't happen either.
Even if the barrier is higher than 2 m.
Yeah, because it doesn't matter, because that's like it's the electric field which matters. But we're gonna see that. We're going to see how that works. Okay, it's coming up. All right. So this is the electron and positron densities at space point r and time t, and they take this form. Okay, I left out some steps here of how do you get that, but I have a derivation. Okay, don't present at the top. But it's kind of fun how you get these really long expressions and then you have to match your creation annihilation operators. Like for every creation, there has to be an annihilation so that otherwise you don't get you get non-zero contribution to this here. Okay, because you have the vacuum on both sides. So we have to calculate these things. And when we do that, we get this. So what does this say? This says start with an electron state labeled by Q, which is it has a fixed momentum and spin, and time evolve it, and then project it at time t onto the positive energy space, and take the mod square. That's the density associated with that, and use sum over all Q. That gives you the electron density, and so this is the Sauter-Schwinger effect right here, and so it's negative energy states. They're positron states, if you like, which basically leak into the electron part of the subspace, like space, and then you get electrons. And here it's electrons that leak into positron, and they're symmetrical these are the same by symmetry. And as a matter of fact, whenever there's an electron that leaked into the positron space, there's a positron that leaked into the electron space, because electrons and positrons are described by the same field operators. So you can't do one without the other. Okay, so that's the vacuum. Now let's start with an electron. See, in my problem, I have an electron, which is going to impact the barrier. So I have to have an electron to begin with. So it's going to be a Gaussian wave packet, right? But I'm going to expand it in terms of these energy, basically the states we have to use here are the vacuum. These are vacuum electron and positron states, because they have fixed momentum. Okay, so we would have some coefficients that would give us a Gaussian here. Okay, and that'll be an electron. So I'm putting a plus sign in to indicate that it's an electron. Okay, so we plug that in. So we have the same expression as before, but we have it here. We have the electron here, and also its adjoint right here. And same over here for the positrons. And then for this part here, we plug in that expressions that I showed before. And then match creation annihilation operators and let the smoke clear and see what we get. And when you do that, you get this. This is what you would get if you just had a vacuum to begin with. And then you get extra term from the electron. So what is this? This says take the electron and evolve it for time t, and then the bit that projects onto the positive subspace, so it's still an electron. We take that density, and that adds to the density that you would have, the Sauter-Schwinger. We'll call that the Sauter-Schwinger density right here. Okay, and then for the positrons, you get interesting thing when you project that electron evolving wave packet onto the negative energy subspace. So now it's and you get a density associated with that, but it subtracts from the Sauter-Schwinger positron density, because what happens is the electron is, how do you think? The electron has leaked into the negative energy subspace, and it essentially blocks electrons. Electrons can't be produced. It's a Pauli exclusion effect, and you get a positron hole here. And the minus sign, when you do the math, it comes out because you get these two electron creation operators that have to be interchanged, and they anti-commute. Isn't it nice when you have somebody who had to learn quantum field theory recently, and now I don't assume you know all this stuff. Like, you might know that, but I had to learn this stuff. Okay. All right, so you might be scratching your head. The feeling there was stuff swept under the carpet there. And yeah, surely there was. Okay. So, I mean, I've got all these electrons and positrons, and they have charge, and they should retract or repel. And I didn't do any of that stuff. So I could have done it, using, say, the first level would be mean field theory level, like Hartree-Fock theory, essentially. And we could do that. it would make the computations a lot longer. But if we did that, we wouldn't get very big corrections because the Coulomb repulsion or attraction, either way, energy is only 1/137 for two electrons separated by 1 lambda bar, which is really small. That's my distance unit. And also they'd have to be really concentrated because they were spread out electrons, then it would be less, which they are more spread out than that. Okay, so, and my barrier is around 7. My barrier height's around 7. So this is actually a small correction. And so this is typical of strong field calculations. You just ignore the interactions between the particles. And the other thing is everything happens here really fast. So the effect of any repulsions would be very tiny because it doesn't have much time, because the electron's just going to go right through. Okay. The other thing I didn't mention, I've left out, electron-positron annihilation. I mean, we have positrons here around the barrier, and the electron's going to go right through it, right? Will they get annihilated? Well, the answer is probably not, because the cross-section for electron-positron annihilation is actually quite small in these energies, in these units in general. And and also the electron is going through that positron cloud really fast. So you can estimate the probability, and it's smaller than 10 to the minus 4. 10 to the minus 4 corresponds to a positron density of 1 positron per cubic lambda bar, which is really, really high. And it's never that high. So the probability of it's going to be less than this. That's an upper bound. All right, so let's look at some results. So here's my barrier now. Notice the barrier is no longer rectangular. You can't have a rectangular barrier. There's no such thing. Okay, because it would be a discontinuous potential, and the electric field would be infinite. It would be a delta function electric field. You can work with that. Sure, you can work around with that, but I figure I might as well, do something more physically meaningful. So I use a super Gaussian here. I'm told this is called a super Gaussian. You can also have any even power higher than 4 as well, but this is good enough. So actually, it's kind of like a rectangular barrier. It's your go-to, I think, choice if you can't do a rectangular barrier. Okay, so this is a log scale. It doesn't show the scale I've said. Okay, and this is my incoming wave packet again. It's a cyan now. I changed colors. Oh, darn. And then this is my barrier, super Gaussian. And then this is time 5. And I've got electron-positron production here. Now, I should point out that the barrier isn't really this. I actually have I ramp it up linearly from time 0. Because you can't have a barrier that's always been there. Because then there would have been electrons and positrons created way back in the past. And they'd still be there. And it'd be a big mess. And so we start off with nothing, and then we can have something. Okay. So at time 5, it's actually, the barrier actually hasn't fully peaked. You can't tell that just a log scale, so you can't see it. But so the peak, barrier is only half as big as this one. But you can see what happens. The electron and positrons get produced at the edges of the barrier. Okay. Like I said, it's the edges that matter. And that's why rectangular barriers are also very confusing, because the edge is too narrow and you get confused easily. It's really easy to get confused on these things. Okay. This shows like how many electrons and positrons we have. So by 150, we're up to 15 plus the one. This one's 16 because there's an electron that we started with. So 15 Sauter-Schwinger electrons. Okay, so here's time 20.
So the curve on the left is the one electron that you sent in.
Yeah, it's coming. It moved a little bit here. It's coming in.
Looks like there's much more under that, but maybe that's the log scale. Then
it's a log scale.
you're thinking about,
It's not as narrow as this.
Yeah.
Okay.
Do you
Um,
keep rising it even as the wave packet gets very close? Do you keep elevating the barrier as the wave packet gets?
Oh, no, no. The barrier just, it stops at 10, which is, we're already at 20. So the barrier is now, I had to ramp it up and I had to do it fast enough so that it was there when anything good happens. And not too fast though, because if you do too fast, then you get a whole burst of electron positron pairs from doing it too fast. So you don't want to do that either. Okay. So, oh, it's really cool here to see what happens. The electrons, you see the electrons, these, I'm going to call these the Sauter-Schwinger electrons. Okay. They're like, they're moving away from the barrier, but the positrons go inside because for the positrons, this is a well. They see a well. They say, well, I'm happy here. This is good. I'm not going to, why should I go anywhere? The electrons, they're repelled. They go away. Also, you do see a little bit of the positrons going away, and that's kind of interesting. How about I just keep that in the back of your mind? We're going to talk about, I'll mention that again. Okay, the positrons do leak out, but on a much, look at this, a log scale. So that's a very tiny amount. Okay, it's leaking out too. And then there's this like wall here. That's the speed of light. Like these electrons are moving. They have a broad, they basically have a uniform distribution. Well, it's not exactly uniform, but roughly uniform from 0 to the speed of light. All velocities are there. So including, and the fast ones are giving you that edge right there. Okay, next. So here we are. Now the barrier, the electron is impinging on the barrier. And here it's emerged. There's the tunneling part. And this line here shows you what, if the particle had moved at the speed of light from its initial center to this, to here, well, to this amount of time, then that's where it would be. But it actually slightly further away because it's superluminal, right? Still superluminal. Okay.
It's only part of the electron that is not the P.
Well, that's of course, but it isn't really part of the electron. What it means is you have to do many experiments, and one electron will actually do it. Okay.
But ultimately, it's the distribution that.
The distribution shows the effect. But again, what that means is that you would do experiments, many experiments, and sometimes it would actually do that. Okay. And that there were interesting points about that I would talk to people later, maybe, about that. How am I doing? Probably close to the end. Okay. So,
I kind of think what you want to do is do this calculation with the incident electron, do it with no incident electron, and see if the final states are at all distinguishable at some time. If there's any way to distinguish those two states, that means you sent.
okay. Well, let's just go. There's the point. Okay. So here's the thing. What we do find is that the electron, these electron density basically just slides. They don't interfere with each other. They're independent. So what it means is that in that sense, the superluminal tunneling survives the putting in the Sauter-Schwinger effect, but it's way bigger. Look, it's bigger by, what is that? About 4 orders of magnitude. Yeah.
Sorry, keep interrupting you. You say they're independent. You have included Coulomb interactions or still not?
No, but it wouldn't matter.
Okay. No, but
It would be slightly different.
well, you have these positrons sitting in the barrier now, so
Yeah.
you've actually suppressed the barrier. And I wonder if that is.
That will be small effect. Okay, all those are small, but they could be done. The only trouble, let me just give a little bit of story. I have a few minutes. So when I first did these calculations, I did them on my laptops, and I did 10 days calculations, 2 laptops, and they were not converged, but I could sort of see where it was going. So I finally got on, after all these years, I got on Compute Canada, as Dan knows. I got on Compute Canada. It was really hard to do, but anyway, it's done now. I'm on it. Okay. And that same calculation, 10 days and 2 laptops, took 22 minutes. And then I could do a 90-minute calculation, fully converged. And that's true looking at. These were 90 minutes on trillion. Okay. So I have to say, it's like amazing. Okay. I do wait till I retired. Okay, so here's the problem. See, the thing is, we're never going to be able to, oh, we're never going to be able to see this thing. It's a look, the Sauter-Schwinger electrons outnumber them by a lot, okay? The tunneling part. So one way of thinking about this is there's like a firewall, okay? You try to do this, there's a firewall. Nature thwarts any attempts at superluminality, okay? Now, I did think about putting in like an additional barrier, smaller barriers, so it doesn't produce more electrons, okay? But barriers, because we could filter out, this has electrons of all velocities, whereas this tunneling electron here, its velocity is about 0.99, well, it started out at 0.992, actually, I did it slightly higher. But it would be like, when it goes through the barrier, it goes up a little bit, it's about 0.994 or something. So if you filtered out low energy stuff, but still, it wouldn't help. I did some back of the envelope, it's just hopeless. You're not going to be able to do that. But it's okay. You get a nice story to talk about. I can come to Toronto and give this story. That's good. Okay, yes?
Give us a sense in physical units, what is a Z in time for electrons?
Yes.
Right. So Z is this is the distance, one-dimensional distance. It's in reduced Compton wavelengths. And time is in, we'll call it zeptoseconds. So 150 is still not very long. It's like sub-picometer. It's really, everything's small. Everything's really tiny or big. It's either big or small. It's relative, yes? That won't really make any difference. Very small difference. We'll even see that in a minute.
You
Okay.
can make a Gaussian barrier instead of the super Gaussian, reduce your fields.
Yeah, I could do that. I don't think it's going to make a big difference, but then I'll have to make it higher because there'll be less tunneling because the barrier doesn't get high until really closer to the middle of it. And it's like, yeah, I've thought about, you're not going to be able to have a perfect result. It's not going to work. Okay. Well, that's okay. You get a nice story. Oh yeah, here I am at my semi-classical. Oh wait, I'm going the wrong way. Okay. So yeah, here we are. Okay. So since I just learned about Sauter-Schwinger effect, pretty recently, and I don't know anything about it. Like, how big should it be? Like, if I change the barrier double, how much bigger? So I needed to understand it better. So here's a semi-classical model of the Sauter-Schwinger effect. Basically what we have, well, I'll go to the next slide, really. Here's the way to think about it. Okay, so this is the line that's at M, and this is at minus M. This is energy. It's MC squared, I should say. C is 1 here, okay? Right. Okay, so we have a barrier, so that shifts this line. Anything above M is an allowed state, right? Because you have to have at least M, because that's the electron rest mass. Okay, so it's got to have that much energy. And then you can have more, and that gets shifted like this. And then also the Dirac C, which apparently you can still talk about it. I wasn't sure, but you can still talk like that. The Dirac C gets pinched upwards. And what happens is you now get these Dirac C states, which are now above the threshold for real states. And this overlap energy region is called the Klein zone. I think somebody mentioned Klein zone.
Bound states of positrons in the well.
Well, that's over here. Yeah, that's the positron picture. What happens is, in the positron picture, positrons tunnel from the positron Dirac C into the well, into these states. And there are 15 of them, actually. Okay, or 16, sorry, 16 of them. And that limits how many Sauter-Schwinger electrons you can get. That's why I get 16 electrons, okay? Like because there's 16 states. Once they're filled, you don't get any more. Okay. And then, so simultaneously, the positron tunnels across and the electron tunnels out. Those are concerted because it's the same thing. It's just looking at it upside down. You're really seeing it in two different ways. That's the way I understand it now. Okay. And then you get these widths. There's a model I showed in the last slide. What thing happens when the here we have an action, an imaginary action that dictates the rate of filling of going across. And it gets really small if there's a big gap between the top, bottom and top states have a bigger gap. Now, here's where we're talking about how sharp the barrier is. If the barrier were not sharp at all, like if it was really like softer, like if these were flatter, then those classically unallowed region intervals would be much wider. And then the probability would drop off exponentially for the effect. So you'd lose the Sauter-Schwinger effect with two. Actually, we want to maybe do that to get less electrons. Okay, let's just move on. I only have I'm already out of time. I guess I'm out of time. But I do have a superluminal barrier. Yeah, just very quickly. Okay, so what if I'm calling this the Dirac smack? I'm going to just send a barrier at the electron. Yeah, so now okay, let me back up. If we could get electrons going through barriers superluminally, then what good would that be? Signaling, you get a tiny effect. It's not worth it, okay? But we all know if you can go faster than the speed of light, there's another frame of reference where you go back in time. That's what I want to do. Okay, I don't know how to do that, so I have to go incrementally towards that. Okay, so let's just say barriers can go faster than the speed of light. Okay, you can ask me about that, how I would do that. Okay, if we do that, it turns out there is a frame of reference. You can't do a Lorentz transformation like to 2 times the speed of light because that doesn't exist. But there is another frame of reference where you end up with, you convert the very fast moving barrier into a pulse in time. It's a pure pulse in time, which is really confusing. And I think there's a lot here that it'd take me a long time to figure out. No spatial dependence. There will be. And because of that, momentum in that frame of reference, momentum is conserved. Keep that in mind. Okay. So here's our results. Let's just look at them. Okay. Here's the results. The barrier is now just barreling towards the electron. Doesn't move now, sitting there. And the barrier is barreling towards it, high speeds. You get a lot more Sauter-Schwinger electrons. Okay, this is really dependent upon how you do things. Okay, and I haven't mastered all of that stuff, but working on it. Okay, let's just go ahead. Here, here's a long time. Okay, I don't see any time travel here. Okay, still working on that. But what is cool, the positron hole gets, in the other calculation, the electron and positron hole were lined up, but this barrier moves so fast, it rips right through, and it rips the positron hole away from the electron. That might be something interesting. I don't know. But the other thing is, I should point out, notice that the barrier went right through the electron. Because remember how there's a frame of reference, related frame of reference, where momentum is conserved now. And so you don't get, there's no tunneling, there's no reflection, because you can't. The electron can't reflect off a barrier moving twice the speed of light. It's impossible. So it doesn't. I guess that's, yeah, made it to the end.